It's going to be a bit easier than homework 1 and homework 2. In fact, homework 2 is sort of the last of the parts of the homework that contain review topics from CS 156. And so all this stuff that we'll be looking at now is sort of very, it will not have any, very minimal overlap with CS 156. And the Kaggle mini project will be released tonight or tomorrow. Again, you have 3 weeks to work on that. Just train your models, submit stuff to the Kaggle leaderboard, and see how well you're doing. Any questions on that? Okay.
Yeah. Should we just self-organize? Like,
I'm sorry?
So the Kaggle group, should we just self-organize?
Self-organize, make friends. You know, last year, people wanted me to have a mixer during my office hours, so I agreed, and then no one showed up. So this year, I'm just going to say, make friends. Yeah. Okay, anyways. So this week, we'll be focusing on learning algorithms and models whose goal is to achieve the highest possible accuracy on some data set that you like classification or regression data set. And in doing so, we'll be looking primarily at decision trees and methods that use decision trees as a response, such as bagging, random forest, boosting, and ensemble selection. The thing to keep in mind about these models is that they're highly nonlinear. These are not linear models, not even close. Okay, so we're going to start with decision trees. So this is a binary decision tree. The basic idea is that you have a decision tree of queries. So for at the top you ask if the input instance is a male. If yes, go down the left branch. If no, go down the right branch. And then each branch you ask a different query until you get to a root node in which afterwards you make a prediction. In this case, the prediction is either 1 or 0. You could do 1 or -1. Doesn't really matter. So don't overthink this. A binary decision tree is exactly what it looks like. It's very simple conceptually. And it's just sort of a sequence of yes/no answers until you're confident enough a sequence of yes/no questions, excuse me, on the input query until you're confident enough to make a prediction about what the instance class label is. Okay? So here for this example that I'll be using as a running example, and you've seen this already in the previous lecture, the x, we have two x features, which is the age and the gender, and the y feature is whether or not the height of the person is above 55 inches. How it works. You have the root, so a little bit of terminology. You have the root node, and these are called the internal nodes. So root node is also an internal node, and these are called the leaf nodes. And the predictions are made only at the leaf nodes. Right. So every internal node is associated with a binary query function, which we could call Q of x, where x is the input instance. And for leaf node has a prediction in this version of binary classification, you have 0 or 1. And so prediction starts at a root node, and you recursively call a query function from the root node, from the current internal node, which starts at the root node, and with a positive response, a left response, and you traverse this tree until you reach a leaf node, after which you make a prediction. Right? So imagine if this is our input. Right? The input is Alice, the gender female, age 14. So we start at the root node. First we ask is the input instance a male person? The answer is no, so we traverse down the right subtree. Is age greater than 11? The answer is yes. We traverse down the left subtree and we answer 1. Yes, we predict that more likely than not, this person has height above 55 inches. Really simple, at least at a conceptual level. Any questions? Okay. Okay, so sort of, given this sort of structure, the next question to ask is, well, what are queries, right? And typically, decision trees are defined using binary queries. So binary query is any function Q that maps input features to 0 or 1. And so the simplest form of binary queries are those that only look at a single dimension or a single feature in your feature vector. So if little d is an index into the dimension of your feature vector, then the basic form of these sort of one-dimensional binary queries is of the following form. So this is an indicator function with whether or not the feature value at the dth dimension is above some constant. So here's some examples. And in fact, all the features here can be represented in this way. All the queries here can be represented this way. You can think of this. You can think of these as sort of shaving off sort of half spaces of your feature representation. Shaving off half spaces of your feature space, right? Like this shaves off a half space of your input feature space, it shaves off another half space with the remaining feature space. So these, you can think of this as representing an axis-aligned partitioning of the input space. And I'll demonstrate this visually in the next couple of slides. So imagine a 2D example where positives are the positive training points, positive points, minuses are negative points in a two-dimensional feature representation. So this is our space, this is our feature space, right, of data. So imagine that at the top level of our tree specifies the following split, right? So each internal node, in this case the root node, is a binary query of a single feature. So in this case, the vertical feature, and it splits the data into this form. So this corresponds to, let's say, the left subtree, and this corresponds to the right subtree. It doesn't really matter if you could flip it for this example. And then at each subtree, we specify another axis-aligned split, which corresponds to a binary query on a single dimension of the features representation. Do the same thing for the other subtree. Now we keep doing this recursively until we decide that this is the tree that we have. Afterwards, we can make predictions, right? And in this particular case, as I'll talk about later on, the prediction you make in a decision tree given training data is the majority class of the training data that falls into each leaf node, right? So if these are the leaf nodes of this decision tree, then within this leaf node, the majority of the examples are positive. Within this leaf node, the majority of examples are negative, and so on and so forth. Right? That's the prediction that we'll make. So given that this is the resolution of our partitioning of our axis-aligned partitioning of the input feature space as specified by our decision tree, this is the best possible prediction you can make for this leaf node. Any questions on that?
How do you choose thresholds for the queries?
I'll talk about training a tree in a few slides. Right now, let's assume that the tree is already trained, and what are the predictions? Right. So, what is the decision tree function class? Right. So, in this course, throughout this course, we've been talking about choosing model classes. What are model classes? Model classes, and up until now, we've primarily talked about linear model classes, right? Which are linear scoring functions, maybe with a sign term if you're doing classification. You can think of decision trees as specifying a piecewise constant or a piecewise static function class, right? All possible partitionings over a feature space, and each partition has a static prediction, right? So the decision tree function class is all possible piecewise static functions, or piecewise constant functions. And furthermore, for for decision trees using single-dimensional binary queries, these partitions must be axis-aligned, right? Which basically means no diagonals, right? No diagonal splits, because you can only split on a single feature at a time, which is the most common way to specify a decision tree. Okay, so let's think a little bit about decision trees versus linear models, right? Decision trees, this is obviously a nonlinear model, right? A linear model looks like this, right? So let's look at this example. It turns out that there does not exist any linear model, so which is just a hyperplane, that can achieve zero error on this data set. Whereas decision trees can achieve zero error relatively easily with this structure. Right, whereas you split here, and then within this subtree you split like that. Yeah.
You have nested linear models?
Right. So you can think of decision trees as very simple linear models that can that is non-zero on only a single feature, right? Right. That's one way to think about the queries. And the one natural question to ask is, can these so you can think of this as a nested sequence of linear classifiers, right? Where I make the restriction that only a single parameter has non-zero weight, right? And also with a bias term, right? And so one natural question to ask is, what about sort of branching on more than one feature at a time, right? Maybe 2, 3, or maybe an arbitrary linear model, right? And the answer is yes, you can. It becomes computationally expensive because now you potentially solve a complicated optimization problem within each leaf node, whereas branching on a single feature at a time is sort of finite, or not, well, it is finite, but it's much more computationally efficient. And if you're going to keep branching anyways, then maybe the efficient thing to do is sort of the better thing to do. But you're right that in some cases you do actually want the splitting criterion to be a more complicated linear function rather than just branching on a single feature. But in practice, if you use decision trees in scikit-learn, for example, it's all binary, single-dimensional queries. At least the built-in off-the-shelf learning algorithms. So let's take a look at this data set. All right. Again, the vertical dimension is irrelevant because they're all constant for all the examples in this data set. No linear model can achieve zero error on this data set. Whereas a simple decision tree that first branch is here and then on this subtree branches like this can achieve zero error. Right? It branches on the same feature twice. So decision trees, and you can imagine a very complicated decision tree being highly nonlinear in this way. Right? Of course, decision trees do have some inductive biases in the sense that they, because they are typically trained by axis-aligned decision partitionings, they cannot easily model diagonal boundaries. For example, if this was my training set, well, I can easily find a linear model that can separate the positive and negative examples using like a linear SVM, right? On the other hand, a decision tree will need to look something like this, right? It can still get zero error, right? But it's somehow much more complicated than this, right? Than it needs to be. And in some sense, the way you can think about sort of how complicated this decision tree is one way to think about it is the wasted capacity of the model, right? Like this part of the decision boundary within the nested recursion of the decision trees completely wasted, right? You're splitting positive and positive examples. Yeah.
Can you is it common to do say something like singular value composition on the data, transform the data to start so that you get some idea of where the axes should be, and then do a binary tree? It seems like you could figure out where.
Yeah, so people have looked at that where they try to somehow rotate the data in a way such that axis line partitionings are more efficient in terms of model capacity. I don't know of any sort of groundbreaking results in that regime, like sometimes it works, sometimes it doesn't, is my feeling. I haven't looked at it closely. Basically what people do, and I should mention that this often is the case because many times the features you use are sort of indicator features. Like if you do text classification, right? I mean the features are just presence or absence of a word or the frequency of a word. And in some sense, there's not much to be gained. So I guess my answer to your question is it depends. Usually people don't bother with it. Like it doesn't help so consistently that people bother with it. Maybe that's the right way to answer the question. Okay, so here's a really extreme example, right? Where instead of just a few data points, I have a lot of data points. So the data is linearly separable, and a linear model can just learn a very simple model that can just split the positive and negative examples, whereas the decision tree boundaries, and I'm not drawing all this partitioning, just the one that sort of sits on the margins, sits on the boundary, can look very, very complicated. Just to summarize decision trees versus linear models. So decision trees are often more accurate, right? Most data sets are not linearly separable. The non-linearity aspect of decision trees is often more important than the fact that you're wasting many axis-aligned queries to get to some nonlinear part of the data. Right? So in some sense, it's okay to waste model capacity, so long as you have enough training data so that the tree you train is reliable. Right? It's okay to train a complicated tree that maybe has some wasted model capacity doing things that are not that useful if you get everything that you need to get. Right? And of course, this requires having enough training data, and we'll talk about this a little bit more later in the lecture. Okay, so you've only seen toy decision trees so far. What do real decision trees look like? Here's a small example of a real decision tree. And if you're interested in what this is actually modeling, you can take a look at this link. Some bottom classification that I don't understand. So people do claim that decision trees are quote unquote interpretable and that you can just read off the decision tree, and that is true within reason. And a professional expert in the domain can still take a look at this tree and internalize it after looking at it long enough. But at some point, for really complicated decision trees, ones that are orders of magnitude larger than this, it just becomes impossible to interpret. Okay, any questions on this? Yeah?
Are there any advantages of decision
So it depends.
Simplified neural networks.
I'm sorry?
They look like very simplified neural networks where each neuron can have only two atoms, right?
Yes, that's right. Decision trees, let's see, what are the advantages? They can be very much faster at runtime. Right? At runtime, you're just tracing down a single, like most of the tree is not active, right, at runtime. Whereas in a neural network, you have to you have to compute all the activations of everything, right, because it's fully connected, if it's fully connected. So it can be much faster at runtime. You can get the same performance, sometimes slightly better, sometimes slightly worse, depending on the data set. So there are some data sets certainly where if you have a very deep neural network, it just is the best model. But there are many data sets where decision trees do just as well, in which case you might as well use a decision tree because it's faster at runtime. Right? If you're training this for a web server or something, and you care about runtime speed, that might matter. And it's also the case that for moderately sized decision trees, people do actually look at the trees. I've collaborated with people who literally took a tree with like a few thousand leaf nodes and just stared at it for a while. And that is, you might think that that's a little ridiculous, but for people who are studying domains where they have very little idea of how to make sense of the data, like they're willing to do that in lieu of the alternative, which is flail hopelessly at the data, right? To help them get insights from the data. Like what are the query functions? Does that answer your question? Okay, so now let's talk about how to train a decision tree. Right, so there's basically two aspects of training a decision tree. What is the structure of the tree, and what are the queries to use within the internal nodes of the tree? Right. So recall that if you think about the training set, right, and how the training set gets mapped onto this tree, every node is equivalent to a partitioning or a subset of the training set, right? So, and furthermore, every layer of the tree. And if you sort of want to be very, very sort of concrete, every cut through the tree, not just and a layer is just the simplest cut, which is corresponds to a complete partitioning of the training set. Right? If you take any cut of the tree, of which a single layer is the simplest case, every training example falls into one of these nodes in this layer, and therefore forms a complete partitioning of the training set. You can also do any cut, like all the training examples fall into either this node or one of these two nodes. That's also valid. Yeah.
So it seems to me that you're kind of assuming that, so like I could have male, age greater than 9, and then on the other side, coming out of male, I could have had blue eyes, right? Like
So I have more features, sure, yeah, more features.
Right. For example, so,
Yeah.
so I don't necessarily have to align things based on age in each layer, right? Am I assuming that's kind of balanced?
The only reason I'm doing this is because it's a two-dimensional example. Yeah. So in general, the feature you choose to split on as a different subtrees will be completely different.
Okay.
Yeah. And that'll become clear as I run through the algorithm. So the root node corresponds to the entire data set. In the splits, these data points correspond to go into this partition, this data point corresponds to this partition, so on and so forth. Okay. So here's a thought experiment. What if we just had one node in our decision tree? This is a valid decision tree. It's just one with no decisions. So it's just the root node. The root node is a leaf node. There are no internal nodes. What this means is it just makes this degenerate decision tree just makes a single prediction for all your data. And no matter what the input features are, I'm going to make a single prediction. So what should that single prediction be if this was the case? Well, it should be the majority class, right? And in this particular case, most of the people in this data set have height greater than 55 inches, so the majority class is okay. So let's go back to our 2D example. That's what it would look like, right? A decision tree with a single root node as the only part of the tree. We just look at it as a classified. The entire training set as positives in this case. Okay, thought experiment continued. Okay, what if we have two levels in the tree? So now we have a single branching decision, right? So we have a root node and two children with a single query. And so if this was our structure, so if we just assume this structure, the sort of the key thing here is, well, what is the query that we should put in this leaf node? That's what we do. That's what we need to figure out from our training set. And then given that query, the predictions of the leaf nodes are sort of just the majority class of the partitioning of the subset of the training data into each partition of the induced by this query. So basically, you just run through all possible queries, and then you pick the one that has the best accuracy. Right? That's the basic idea. Can anyone tell me, roughly speaking, how many queries, if I were to exhaustively try all possible queries, this would require? Silence is deafening. Okay, the homework 2 is a little hard. I get it. So the number of possible queries is the number of possible. Is the number of possible data points. In the worst case, the number of possible data points times the number of possible features. So if these are all real valued features, then there are the number of unique splits for each feature is equal to the number of data points, right? Since we have 2 features, then it's 2 times the number of data points. And those will become clear in this example. So this is how suppose we want to build a decision tree with just a single split and 2 leaf nodes. What the training algorithm would do, it would look at all possible partitions along the vertical feature and all possible partitions along the horizontal feature. So consider this partitioning. Look at the accuracy of the 2 leaf nodes. If it had the predict majority class of the 2 leaf nodes, try a different vertical partitioning. Excuse me. Compute the accuracy. Try a different vertical partitioning. Compute the accuracy, and then the number of unique vertical partitionings, assuming that this is a real value feature representation and all the training data points have a unique value for this feature is equal to the number of data points. Right, then after we try the vertical feature will try the horizontal feature, do the same thing. Obviously, a computer can do this much faster than I can, but you get the idea. So number of Hausdorff squares equals d times n, where this is in the worst case, by the way, where d's number of features and n is number of training points. And after we loop through all of these d times n queries, we choose the best one, right? According to some decision criterion that, roughly speaking, corresponds to accuracy. Any questions on this before I talk about yeah?
So for real value features, then you would discretize them, and then.
Yeah. So one common approach is to obviously not try all possible. You would try sort of intervals. Like there are many tricks you can do. So you could, it's easy to sort of intuitively see why, like if I try this split and then I try this split, somehow it doesn't make a difference, right? In terms of accuracy. So you could either there are many ways to sort of choose a smaller subset of splits. One way is to just look at intervals, right? One way is to look at percentiles. Like you might have some outlier features, in which case you don't want to do intervals. And the specific way you want to do that in order to gain computational savings is sort of depending on the distribution of the feature values, right? But that's certainly something that you can think about. Okay, so typically when people, when decision tree learning algorithms try to figure out which split amongst the splits that they've tried is the best split to be chosen, they do so using a notion of impurity, what they call impurity, which is at a conceptual level basically the same thing as a loss function, right? They just call it impurity in many of the literature. And so basically, the most direct impurity function is 0, 1 loss, right? So if S prime denotes a subset of the features induced by one partitioning or one leaf node, then the leaf node of that, then the loss of that partitioning is simply the choice of a constant prediction, 0 or 1, and you can do -1 or 1 depending on how you represent the labels. That minimizes the 0, 1 loss, right? Just the 1 minus the accuracy. So if this was my leaf node, then the 0, 1 loss, then I have to map the optimal prediction is to predict 1, and the 0, 1 loss is 1. Right? And then if I were to do this split, right, then the 0, 1 loss of this side is 0, and the 0, 1 loss of this side is 1. So here's one problem. In many ways, I mean, obviously there are more intelligent splits you can do, but even here, right, somehow this is somehow better than this, right? But it's not captured by this impurity function because the impurity reduction is somehow, by this impurity function, this decision tree is no better than this decision tree, even though this obviously is, although we can find a better one, right? No benefit from this split. Right. So let's try another one. Benefit. And of course, in this particular case, a single split can lead to reduction 0, 1 loss, and so we get a benefit. Right? So this is the training goal of decision tree training, is to find a decision. So again, we're still just talking about a single query, although this concept generalizes. Find a decision tree with low impurity, and if the decision tree is a single query, find a query, choose the query that gives the lowest impurity or the greatest impurity reduction from just having a root node. And you can think of impurity over leaf nodes as equivalent to some loss function, some training loss, right? Because it's the impurity over leaf nodes enumerates over all the training examples because it defines a complete partitioning. Of course, just like in the linear model case where optimizing for 0, 1 loss is very difficult because 0, 1 loss is flat or discontinuous everywhere, we get a very similar style of issue with 0, 1 loss as the impurity measure, right? So consider this example. It turns out that no matter what split you choose, the 0, 1 loss, the impurity, if your impurity measure is 0, 1 loss, no matter what split you choose, the impurity loss, the impurity reduction will only be 0, right? Clearly, this is a better tree than this one because if I just do one more split, I'm done, right? But if I don't know that, if I don't think ahead that I'm going to do another split, and I just want to choose a single split that gives the best reduction in 0, 1 impurity, then my learning algorithm is actually indifferent towards either of these, right? It's actually indifferent between splitting and not splitting, right? And this again alludes to the fact that 0, 1 loss is somehow flat and discontinuous everywhere. So, just like in the sort of linear model case, we're going to look at surrogate impurity measures, which is somehow more continuous and therefore can model the fact that even if our accuracy isn't going up at the moment, somehow the quality of the tree is getting better. Right? And one way to do that is to sort of think of the confusion of this, think about some notion of confusion of the leaf nodes, right? Here, with a single leaf node, we're confusing one negative example with 5 positive examples. With this split, with this subset, we have no confusion. And with this subset, we're confusing one negative example with one positive example. Somehow that's a good thing, right? Even though the accuracy of the final prediction isn't getting better, the fact of the matter is this tree is less confused about its prediction than this tree is. It's somehow more confident, right? And so here's one version, one way to measure that sort of confusion or confidence. And it's Bernoulli variance. It's simply given a sort of a subset of the training data called S prime. It's the Bernoulli variance is basically the proportion of positives times the proportion of negatives. That's what this formula is. And we're not going to. Bernoulli variance is normalized by the number of training examples, but we're going to do unnormalized, so that it expresses a sum over the entire training set. So the worst impurity, or the worst purity, the worst one is when you have a training subset, a training partition with 50% positive, 50% negative. This number is going to be quite large. And when you have sort of perfect purity, zero impurity, is when you have all positive or all negatives, in which case this value is 0. So this is what the curve looks like. And again, here I'm not multiplying by the number of training examples. By the number of training examples, we're just assuming it equals 1. In practice, it's this curve, the y-axis of this curve is scaled by the number of training examples. But this is what it looks like. So at the extreme ends with perfect purity, you get 0 impurity. And then when at maximal confusion, you get the highest impurity. Any questions on that? Okay, so now suppose now we're using Bernoulli variance as a measure of impurity. Now we can sort of look at this example again. This is the same example where we're splitting on 0,1 laws as impurity doesn't do anything productive. So now the impurity of this is, this value computed according to this, computed according to this formula. And again, I'm ignoring some sort of scaling issues. It should be clear from context, scaling issues. So we split on this. This is the impurity, resulting impurity of the two sides. So here, this is the resulting impurity of two sides. So clearly, this is according to this impurity measure, this is a better split than this is. And power on. All right, go. So Bernoulli variance is not the only measure of impurity. Although another one is called entropy, which is a measure of how much information is encoded in a probability distribution. And in this case, the probability distribution is simply a fraction of within a training subset, the distribution of positives versus negative examples, and it's defined by this equation. And it looks like this if you were to plot it. Entropy reduction, so choosing a split that reduces the entropy, so an AB split of S prime that reduces the entropy of the measures the reduction entropy compared to just the entropy of S prime is also known as the information gain. And this is I believe this is the most popular measure of impurity that's used in practice in decision tree training. Another one is the Gini index. It just looks, here's the formula, where this again is the fraction of positive examples in S prime, and it looks like this. In fact, almost any measure of impurity that gets